Hi everyone, welcome to tutorial 77 of our introductory Python for image processing tutorial series. In the last tutorial we looked at random forest, and in this tutorial let's have a quick look at support vector machines. And these two are, I would say, the most commonly used traditional machine learning algorithms for image analysis, if you want image analysis, but also for in general for data analysis. So let's have a quick look at what it is and then jump into the code to implement this on the same breast cancer data set that we have used in the previous tutorial for random forest. So SVM stands for support vector machines, and the goal of SVM is to find a hyperplane. Well, hyperplane is basically a plane or let's say if you have two data points in two dimension, like clusters, just draw a straight line. So in this case, the plane is a straight line. If you have 3 dimension, if you have n dimensionals, that's why it's called hyperplane. Okay, it can be curved, it can be straight. Okay, so our goal with support vector machines is to find this plane that separates data points into respective classes. If you have n-dimensional space and you have multiple classes, and separate this into these many classes. So if you look at this data, this graphic down here, you can see there is one cluster on the left-hand side and the other cluster on the right, and you can separate them with this straight line right there. Okay, you can separate them with that straight line, and this is think of this as the line, the front line, right? I mean the front line that's actually going through these data points, on the edge. Same thing on the other side, and this is right in the middle. Now the question is, for this same data, is this the best hyperplane, or is this the best hyperplane? Exactly what I'm doing is using a different data points in the front lines, okay, on the edges, and then looking at the center between these two. Okay, so obviously, as you can see, this is the maximum margin right here. So this would be preferable than the other one. So the whole point of support vector machines is to find this hyperplane, and these data points that are on the edge are called support vectors. Well, it's not just these ones. You can actually add extra weight to these, and you can actually define how deep do you want to go from the surface in terms of their contribution towards defining the hyperplane. So all of these can be defined as part of your Python code when you're doing support vector machines, but most of the time the default values work fine. Okay, and these are the data points on the surface. Now, every time you do machine learning, it's trying to minimize some loss function. So in this case, think of the loss function as maximizing the distance between these two planes right there, or support vectors, and hence the name support vector machine. Okay, and the implementation is very simple. It's again part of scikit-learn.svm, and there are many variations of support vector machines. So please go ahead and look at the documentation. Like I mentioned earlier, you can actually provide a whole bunch of parameters that actually define, for example, I'm trying to see which one makes sense for now. I think one of these kernel is what type of kernel? Is it like a straight line, or what type of kernel would you like to use to define this surface? And again, I don't want to guess right now. Every time I apply something, I just go to the documentation, make sure what my thought is the right one, and apply the appropriate parameters. So now time to jump into the code and work on the same data set from last time. So I'm not going to do a lot of explanation here. I assume most of you watched my random forest video. Again, this is the breast cancer data set from Wisconsin, where we have one outcome diagnosis, either it is benign or malignant, and a whole bunch of attributes that we are going to fit. Okay, so let's go ahead and input, and we know that there are no null data points, so I'm not going to run that line, and I'm going to rename the diagnosis as label because I don't like the title diagnosis. Again, optional stuff right there, and let's just do one plot so you can see how the data is divided. Malignant 200 some and benign 350 some, so we have more benign than malignant data points in this case. Okay, so now let's go ahead and change the labels of M and B. Like if you look at the data set, our labels are M or B, right? So let's change them into 1 and 2 because that's how computers work. They work better with numbers. So let's change them, and the way you do that is just define a dictionary for B equals to 1, M equals to 2, and replace it, and it should be all set. So now if I open my data frame, you can see the label column has been relabeled. Okay, now again, same steps as last time. What is our y? Y is always the prediction, x is always the input, right? So y is the dependent variable, x is the independent variables. So we are fitting x with this machine learning algorithm to predict y. So our y is the column called label, and our x is everything except for label and ID. And again, I defined this in the last tutorial. ID is just an ID of the patient, so we don't care about it because it's not going to help us predict the outcome. And label is just the outcome, so we're not going to fit it. So let's drop those two, and we need to scale our values because our x values range from 100th or sometimes 1000th to all the way to 1000. Okay, so there is a 6 orders of magnitude difference between the smallest number and the largest number. So by normalizing, we bring everything to the same scale. Now we are going to split this into training and testing. Again, we did this quite a few times, so I'm not gonna dwell some time on it. Now, support vector machines. Again, there are multiple ways to use it. There is sklearn.svm, import svc, and I'm going to use linear svc instead of svc. Okay. Again, you can try SVC with linear kernel and a couple of other different types of kernels, which you, I believe if you use linear, you'll end up with a very similar result. But let's go ahead and import the entire SVM. And within SVM, I'm going to use linear SVC. And the only parameter I usually change is maximum iterations, because sometimes the problem may not converge. And there will be a default maximum iteration as defined by the documentation. Go ahead and look at it. But sometimes it comes back with a message saying that, okay, the problem didn't converge. So I'll just give 10,000 because I know it's usually pretty fast. Okay, so once the model is defined, these are the steps we have done exactly at least twice with random forest and with logistic regression. So hopefully you're following very well. Okay, so our model is defined. Now I'm fitting it to the actual data, but obviously not the entire data, to the training data set, so I can predict it on the test. You see how fast it went for training? So now we are predicting, and the prediction is done, and there is the prediction. And where is our original y test? Right there is our original. Looks like it's doing pretty good. So let's actually print out the accuracy. So to print out accuracy, we are going to use scikit-learn metrics. So metrics.accuracy score. And let's go ahead and print this out. And our accuracy is 97.3%, which is, I would say, very good. Maybe you can try to do some balancing of data sets by dropping some of the benign ones to bring both at 200, or you can enhance, or you can copy some of these and enhance your malignant ones to match 350. And that improves your accuracy a little bit in case you're looking at ways to improve this analysis. Okay, so now let's go ahead and do confusion matrix. Again, this gives us an idea. So 70 out of 72 benigns are accurately classified, and 41 out of 42 malignants are accurately classified. And if you would like to print out these values as a percentage, 97.2 and 97.6. So this is how support vector machines is, and both random forest and support vector machines are for most applications equally good. And random forest usually works better with data that's imbalanced. In this case, they're not that imbalanced. You have like 200 data points for malignant, 350 for benign. They're kind of okay. But what if you only have 40 for benign or malignant, one of these, and then 1000 for the other? This is usually the case with a lot of data sets. For example, if you're looking at failure analysis, you'll have a lot of data sets where things did not fail, but you only have few data sets where things fail. So when you try to fit it, it does great on the large data set, but it fails on the small class. So you may want to balance these classes and all that to improve your accuracy. Okay, so this concludes our support vector machines, and starting next tutorial, it will be a bit exciting because we'll take a bunch of images and we'll label them, and we'll take those labels and we'll train random forest or support vector machines to segment this entire 400, 500 images. And you can save that model to segment any of the future data sets, or you can take these segmented images and train a deep learning to create even more robust model that you can use for other data sets. So all of that is coming up starting the next tutorial. Please stay tuned, and thank you very much for watching the videos, and please subscribe.